And I'm walking around this place thinking I've got a huge
Markov chain
for a step
model.
Secretly, you're not a
Markov chain.
Let's play a game.
If you were a chick, who's the one guy you
Subscribe to Matthew Haynes.
What? Did we just become best friends?
Yup!
Last time, we had explored the exciting world of image generation and added it to our chat app. What we came up with worked, and it was good fun, but it can be better. How? I'm glad you asked. You see, right now we have two paths, one for images and one for text, and they never interact. But what if that wasn't the case? What if you didn't have to choose? Let's get a sneak peek. There was a subtle but important detail in that sneak peek. Did you catch it? Notice how we got back both text and image responses, but we didn't explicitly ask for either one. This may seem like a small detail, but I assure you there's more than meets the eye. To pull it off, we had to use two language models and an image model all together. If you're familiar with Mixture of Experts, I kind of like to think of it as Mixture of Models, or MOM. Now, I say this kind of jokingly, it's not like I have a paper on archive or anything, but I think the point kind of stands. And also, just to clarify, this isn't the same thing as multimodal. And yes, of course, the brilliant folks at FAIR have been working on the chameleon models that can do pretty much anything to pretty much anything. But to be fair, that's not the norm in the open weight model space right now. So what's actually going on here? Well, our strictly image path remains unchanged, but the default path has a lot more going on. First, we're going to add a small language model in front of everything, in this case Llama 3.2 3 billion. It's going to classify the user's message into wanting either an image or text response. Technically, our larger 8 billion parameter model could work for this, but as this is a simple classification task, and it blocks the later stages, I wanted it to happen as quick as possible. Llama 3.2 1 billion could work as well, but in my limited testing, 3 billion seemed a little bit more accurate. Also, you could even go the traditional ML route with something like BERT. In my case though, 3.2 3 billion had a good sweet spot of not needing to fine-tune it with a dataset and still having good accuracy and good speed. One more thing, for this classification task, we're actually going to provide a JSON schema to the model to constrain its output. A quick word on that. Constrained outputs, or response formats, or structured outputs are incredibly useful and incredibly powerful tools. Constraining the output to a schema makes the LLM's responses more predictable and consistent. And it also makes it easier to work with because we don't have to write our own cleaning or parsing steps. Also, by defining a schema, the LLM is less likely to make errors or make stuff up, because it has clear guides about what it's supposed to generate. Now for our stack, we can't guarantee it's going to work 100% of the time. I'm actually kind of curious to see how OpenAI pulls it off behind the scenes, but it's certainly better than writing some regex. After the classification step, if the user wants text back, it's business as usual. But if the user wants an image back, then we'll actually use the language model to generate a prompt based on the user's message, and then feed that into the image model. Why? Well, in my testing, putting something like cat into the image model versus putting a prompt that the LLM generated based on cat provided more interesting and rich results. Keep in mind that the strict image path remains unchanged, so if we wanted to manually prompt the image model, we could do it that way. After we have our generated prompt from the language model, we're going to feed that into the same image pipeline as the image path, and then return the results back to the user. And that's the gist of it. Our toolkit is going to be the same as part 5 with the addition of Llama 3.2. Let's go ahead and dive in. First things first, let's go ahead and set up a copy of where we left off in part 5 as part 6. So that's what we have here. Next, let's do some quick code cleanup. So if we take a look at the diff, come on. What we're going to do first to make our lives a little bit easier is have a local Docker YAML, and then the actual Docker Compose YAML will just be what we use on our cloud server. So the local YAML is going to be pretty much the same, but we're just not going to have any GPU mappings because, at least for me, I'm not using NVIDIA on local. So we're no CUDA, no GPU mappings, and it's aside from that pretty much the same. And for our Docker Compose, like I had said, it's going to be what we were using originally. So in this case also, we're going to make sure that the web service is going to wait for the inference service to be started. And that's that. Next up, we've got quite a few changes. Let's dive into them. So first things first, we are going to be using the L12 model for embeddings. In some testing I've done, it seems to have better embedding performance, semantic search performance compared to the L6. It's going to be a little bit slower, but the embedding generation isn't really the bottleneck in this stack anyway. So a little bit better performance and in theory, a little bit slower. Next up, we are going to, in our Docker files, we're going to cache the embeddings model. So Infinity is going to download the models and it'll store it in the Hugging Face cache. But we didn't have that volume mapped, so it's going to do it every time. So we're just going to add a mapping for that so it doesn't bother trying to download it every time. After that, we are going to do one more thing for kind of overall setup. In our entry point where we're downloading the NLTK, we had forgotten to download some other ones, Perceptron, etc., and it was throwing an error. So just make sure we're downloading all the right stuff. And then moving right along, we're going to, let's take a look at this one too, because it's overall. So for deploy, we're going to sync the environment.example, but not the environment file. Because when I'm on the cloud server, I'm sometimes tweaking things and I don't want my local environment file to overwrite that. So the very first time you'll have to create an environment file from example, but after that, it should be fine. And then that way it's not getting overwritten every time you sync the code. So after that, let's take a look at our app file. And again, these are just some code cleanup refactorings. We haven't gotten into the pipeline classification, any of that kind of stuff just yet. Yeah, so we're gonna rename the vector store class to content store because I think that better clarifies that it's not just for vectors, right? We're also storing our text snippets there, and we're doing keyword searches in addition to nearest neighbor searches. Also, we'll dive into this when we get to the diff for the content store class, but we're going to be doing some better typing for our interfaces when we're passing stuff around. Yeah, and this diff is pretty much just going to be that. We're also going to be commenting out and marking that old prompt route as deprecated. This is the one that was doing the non-streamed response. And realistically, we're not going to be using that. We're always going to be streaming back the response. So no point in having both of those around. And then, yeah, content store got renamed and open search config class. So let's take a look at that actually next instead of some of these other ones, since it's top of mind. In our content store, which is going to look quite different. I don't think I can, yeah, I can't dual mix. So content store is what vector store used to be. Not a lot of stuff changed here functionally, but there is some interesting stuff. So first thing, we're gonna create a data class. And all this is doing is just kind of defining the shape of the config that we expect. So it's a little bit easier and a little bit more consistent to pass around instead of just doing a bunch of parameters. So you can see here hostname port. Auth is going to expect a tuple of string for username and password, SSL, and verify certs. Also, we're going to be using some class constants for things that are realistically never going to change. So index name, search pipeline, pipeline settings, base query, that kind of stuff. So move those up to a class constant. What also has changed is our index settings is going to be a cached property. So the reason why we're going to use a cached property for this instead of a class constant or just a regular function is we can kind of get the best of both worlds. we have to do a calculation here, or rather we're calling the embedding service to get the dimensions right here. But we only have to do that once when we initialize this instance. So we're going to use a function for this because we do have to call this, but we only have to do it once. So that's why cached property comes in, because we can do it once and then from there it's cached and you don't have to run these settings ever again. So it's kind of nice to have this as a cached property. And this is actually going to get called in the insurer setup. And then from here, again, it's pretty much the same, right? There's nothing functionally different. There was just some, refactorings and cleaning stuff up. The rest of it's pretty much the same. We're taking our OpenSearch config data class here, but then from there it's pretty much the same. And then again, we're just calling some stuff. It used to be, instance variables. Now it's class constants and cached properties, and the rest of it's pretty much the same. Let's go ahead and move on. Let's actually do app LLM, because I think that will change. We'll do app LLM, then LLM HTTP client. Let's do that the other way. HTTP client. All right, so this is a bit cleaned up as well. We're going to expose the temperature if we wanted to change it. So that's a small detail, nothing super substantial there. The GET responses and GET response streams are changed quite a bit though. So as we were working on some of the other examples, we were starting to get some cruft, and we had GET response stream, GET chat stream. And they were all kind of doing the same thing. The real difference was whether or not it was getting a list of messages or a single prompt, right? That's kind of what it boiled down to. GET response was, I think we had it as a single message, and then GET chat response was a list of messages. And there's no really good reason to support that. So we've kind of cleaned this up. So now LLM response is going to require a list of messages, and it's going to return back the API calls response. And then stream likewise is going to list the messages, and it'll come back. So also what we've done is any common code between the two, we've just placed it down here in a helper, right? Because the headers, the body messages, where we're injecting the system prompt, that's all going to be the same, right? So let's not bother trying to do it twice. So you can see here, get the response stream. We're going to prepare the request, right? So, and that actually is going to return a tuple, of the headers and the body. And parse server sent event, it's a little bit different, just a little bit of cleanup. And then we also have a helper to extract the content from the response. So originally in our app LLM is where we were kind of going through this nested structure to get the actual response back and, kind of pulling it out. So we're just going to do it here, and it's optional. So you can, we have it set so that you can optionally do that. And likewise for the server sent event parsing, it's a little bit different, sort of cleaned up. And then we can see in our stream, we are, return parse content, and that's what's gonna extract it out, and it defaults to true, so that when we're getting the content back in our app LLM, we're not having to kind of weed through the HTTP response from the API. So app LLM is using content store. That's just a name change. The prompts are handled a little bit differently. Previously, we were just kind of adding them one by one and sort of hard coding them. Instead, what we're going to do is just loop through them. We're going to look at the prompts directory, and anything that has a J2 extension. I mean, there really shouldn't be anything in the prompts directory except prompts, but anything that has a J2 extension, we're going to load it up as if it were a prompt. And then we're just going to have a prompts property that contains them. System prompts a little bit different, because we'll always want that. But everything else is it's going to be loaded up that way. And then we have to call it through a prompts attribute. So yeah, you can see the diffs here are a little bit difficult to navigate. So let's actually pull up the code itself and take a look at it that way. And LLM HTTP Client, this is a little bit easier. We'll just do this super quick so it's not cluttered up by the diff. So we're getting the headers and the body from prepare response request. We're getting the response back, and then we're gonna extract the content from it using that helper. Stream is the same thing, right? Prepare the request, get the streamed response back, and optionally extract the decoded content from it. So it's a lot simpler in that we're only supporting 2 response methods, either a stream or not, and then we've just got some helpers. So this is significantly simpler compared to where we left it last time. And then app LLM. So what we're doing here is, again, we're just gonna look at that prompts directory, loop through all the files, pull them in, same code as before, it's just now done in a loop. And then it's saving it to a prompt templates property. And then we've got both the string, but also the template object that we can invoke. Some of the templates we don't want to actually pass variables into, like for example, the system prompt, because there's no variable interpolation needed. It's just textual content. And yeah, for helper's sake, we're just setting the system prompt directly. All the other ones are going to have to be called. And then for app LLM, we're cleaning this up a little bit as well. So similar story as to the LLM client. We had, kind of had some helper methods that were getting a little cluttered because there were some stream, some non-stream. So we're just cleaning it up a little bit. And let's take a look at what we have left. Yeah. So if we just collapse all of these and kind of quickly go through it, we can see what we have left is get a response, which is going to take an input and give you back the response, right? And it's significantly cleaner because we're just going to call a helper, but given an input, optionally wrap it with rag, where it's going to use the context, pass that as the prompt, get it back. Stream, same deal, where we're going to wrap it if it's rag, and then we're going to call this HTTP client, get the response back. And we've still got that helper to remove template tokens and stuff like that as needed. Although now we've made it a static method because it's in isolation. It doesn't require anything from this class. So you notice we're not passing self in, because if we wanted to, we could rip it out entirely and it would still work. So we've also got chat summary, and that is just going to call the chat summary template, but likewise after that it's going to work the same as LLM response, where it's just calling this. So how this works, pretty much the same deal, right? We're going to take our content that's passed in, and we're going to get a object for it that's basically going to be that dict, where its role is user, content, etc. We're going to pass that in to get a response from the LLM, and then that's pretty much it. Rag prompt is the same thing. It's just going to get the context and render the template with that relevant context. Relevant context is going to query the content store, render last message with rag prompt. It's just going to, given a list of messages, swap out the last message for a ragged up version of it. And then we've got a log helper. So structurally or functionally, it's doing a lot of the same stuff. It's just we've kind of cleaned up the functions. We've got less overlap. In the part 5 version, we had services, app LLM, and LLM HTTP, right? So LLM HTTP, we had get response, which takes a single prompt, get response streamed, single And then we've got chat response as a list, and there's code duplication. And then likewise in part 5, we're declaring these templates individually. We've got LLM response for a string, LLM response for a string. Stream is going to take a list. So it's just kind of, it was getting a little cluttered. It was getting a little crufty. So we've just simplified and cleaned up our code base into only the things that we were actually using. And that's most of the changes for App LLM and LLM HTTP Client. Just again, really try to simplify and clean up our code base now that it's consolidating. And then Chat Manager, these are probably going to be superficial changes. Yeah, that's right. It's a very minor change. So because we removed this LLM response, chat response from that helper, we're just getting an LLM response, and LLM response expects a list anyway, so that's consistent. And that's it for that one. And that's it for this set of diffs. And let's take a look at the next one. Let's take a look at our Svelte code. Similar story. We're getting to the point where we kind of know how the app is shaping up. It's all fun and games to just kind of quickly whip things together, prototype it real quick. But, long term, you kind of do need to clean things up and be a little bit more diligent. So the main story here is we're going to be defining some custom interfaces or types in our code base for Svelte. Well, first things first, what we're also going to do is make sure the app element exists on the page before trying to make a Svelte app out of it. For example, our 404 page isn't going to have our chat app on it. So don't try to, bootstrap the Svelte app. So look for the app element. If it exists, then we want Svelte on that page. Then we'll go ahead and do it. So that's what's changed here. Just a small thing. And app types. So what we've done here is we've mirrored some of our models from the back end, and we've also kind of clarified the shape of objects that we want on the front end. So some of these, just for clarity's sake, we'll probably do further refactoring, but we've got like backend chat message that's distinct from like chat message that's used on the front end, slightly different shape. So we've got our roles, enum for roles, chat message, right? These are simple from the back end. Our initial chat state, that gets loaded from the server as well. We've got an enum for whether, who's the author of the chat message on the front end. We've got our interface for the chat message structure on the front end. We've got our enum for the toast states that we're working with. Enum for the toast message structure. Interface for the toast message structure. Interface for, the citation and source, and interface for our input commands, our slash commands. And what that allows us to do is in our app code, you can see we're going to import the enums and then import the types, and then we'll reference those. Also, there's a naming conflict, so we'll call chat message.svelte, the chat message component. Yeah, so you can see here, we're just going to reference that, and it'll allow us to have better type hinting throughout the code base. It allows us to have better autocompletes, and it's just going to make it, a little bit easier to reason about and make sure we're a little bit more consistent. Yeah, and you can see here we've gone like, for example, we're using these enums, right? We can just do chat message author.user as opposed to typing out you. And then we can refer to that throughout the code base. Functionally, it's pretty much the same though. So all this is doing, it's not adding new functionality. It's just kind of cleaning up our code. And again, making it more consistent and I think easier to reason about. So yeah, that's pretty much it, right? What that also means is when we're passing stuff into our components, we are going to use those types as well. So if we look here, before we were passing in the props individually, Now we can just pass in an object, but because we have defined the shape of it, we know it's going to have a title, body, and state for the toast message or any of these other ones, right? So to quickly breeze through that, toast, right? We're just taking in a toast type or interface, and we know it has those properties. Likewise with source, and likewise with chat message. So yeah, I think that cleans it up a decent amount, and it again allows us to be better structured, and it's a little bit more consistent. So just some quick cleanup. It's good to kind of clean it up as we go along and make sure it's not too crufty. All right, now for the thing you've been waiting for, let's take a look at the actual changes to classification and running these things. Okay, fun stuff. So what we're gonna do, as I had mentioned, is we're gonna run a small language model. So you can see here, we're gonna copy our config pretty much for what we had done for the inference API. And now we're just running another instance that's a small model. Let me actually pull up the Docker file to better express this. So you can see we're adding a brand new service. So Llama C++, at least right now, you don't want to do hot swapping. It can't do hot swapping, and nor would that really make sense. So we're actually going to run two instances. So we're going to have inference and inference small. And then inference small is going to be very similar to inference, just with that smaller model and smaller context, actually, because we want it as fast as possible. So environment file, we can see inference small is going to be the service name is kind of what the URL is in Docker. And then we're also going to be using Llama 8 billion for our regular inference, and then Llama 3.2. This has 1 billion. On the server, it's 3 billion. You can use either. I found that the 3 billion is a little bit more accurate. But aside from that, it's pretty much the same, with the context size intentionally constrained. And that's it for that. And that's it for Docker. Again, it's just the same thing, just passing in those environment variables. So we're running 2 instances of Llama C++. Our setup script for the server is pretty much the same. We're just going to add an additional model file. So that's going to be the same. And our config, all we're doing is adding small inference. Nothing too fancy there. The fun stuff is going to be in our app. Let's take a look at this. So this is a little bit different. So you can see what we are doing is for our app LLM, we're adding in this small inference as an option, or as a property, I should say. And then that way, when we get into the prompt stream, you'll notice that the very first thing we're going to do is use this classify message. And then from there, it's going to be, if it's an image, run through the image prompt, else run through the standard text that we've been doing before. And then it's pretty much the same. Looks a little bit different, but that's essentially what's happening is if it's an image, image pipeline, if it's text, regular text. And the image response is just a little bit cleaned up, but functionally the same, so we don't have to worry about that. Let's pull up all of this stuff. So if we look at our app LLM, we have added quite a bit. So what we're looking at is we're going to have response types. So this is just going to have a classification for if it's an image or if it's text, and that's pretty much it. I was trying to get clever with using an enum for saying image, text, and maybe down the line audio, video, and then later on dynamically creating this data class from the enum, and I actually got it working, but it didn't have type support. So that was kind of a bummer, and maybe I'll come back to it, but for now, I'm just gonna have this simple response type flags data class, and not an enum for it. So we're gonna bring this in, and again, this is gonna be if it's an image or if it is text, and that's gonna be used with our response. So we're bringing in the small LLM inference endpoint. We are going to need the classifier response format. Response format, this is how we tell the small language model what format we want. This is going to be our JSON schema. So you can see here, we are going to take in these response type flags. So if is image and is text. So those are the only two fields we care about. So it's going to say, it's going to be a JSON object. That's going to be the type. The schema is going to be basically is image, is text as booleans. And we're dynamically generating this from our response type flags, but we'll come back to that because we're going to use it also after we get the message back. So it's going to be a JSON object. It's going to have the only those two properties, and then it's going to say both of those properties are required. Now you may be wondering, why do I have is image, is text, and both of those properties, as opposed to doing something a little bit more sophisticated where it's just saying like response type and then maybe :image or :text or something like that. Probably could do that. In my limited testing, having explicit booleans for both types seemed to work a little bit better and a little bit more consistent. So for now, that's what we're going with. So we're going to pass this response format as a property to our LLM call. And again, this is, if you look in the Llama C++ docs, they kind of explain it, although it mirrors OpenAI's spec. So then when we call classify message, we are going to pass a system prompt that says output JSON. That seems to be important. And then we're going to use our classifier template. And if we take a look at that, here, you are a message classifier that determines whether a usage message requires a text or image response. Analyze the intent and content of each message carefully. Classify the message according to whether it needs a text or image response. And then we're going to pass in the message, and then we're going to have some examples. So using these examples seem to help. So image of a cat is going to be an image, whereas what is a CPU is going to be text. And then some additional guidelines. So this is our prompt that we're passing in. And if we go back, so we're going to pass in that prompt with the message. We're also, again, we're going to pass in these classifier format. And again, it's cache property because we only really need to do this once. So yeah, so you can see here response format gets passed in here. And then we get the response type back. And keep in mind the response from our message, like if we put in image of a cat, all this classifier is going to do is return that JSON object that says is image true, is text false. That's all it's going to give back. It's not going to give back anything else. So then we're going to parse this JSON, right? That'll get us, our dict or whatever. And then we can pass this into our response type flags data class. And because the JSON has the same properties as the data class, we now can call our data class properties. So let's go back to app LLM and see how that kind of works. So we get the classification, and now we can call .isImage because again, this is our data class, and isImage is a property. So from here, if it is an image, what are we going to do? Well, we've got one more step here. What we want to do is generate a prompt using the language model from our original message, and that's what this is going to look like. So we're just going to take the user's message and run it into this generate diffusion prompt template. It's going to look something like this. Write a prompt for a diffusion image generation model based on the following message. Respond only with the prompt. And this actually seems to work kind of well. And then from there, it's actually pretty simple, right? Our LLM's gonna do that. We get that back. And then from there, we're back into our image pipeline, business as usual, right? So we've got this generated prompt that gets fed into the pipeline, and then we're just generating a chat message. And that is pretty much it. Again, the rest of it, there's a lot of noise in the diff, but that's just, formatting, and there's nothing really substantive there. So let's close that. Let's close app LLM Pi. I think we covered it. Yeah, formatting changes, some type hinting, a little bit of type hinting changes. Nothing too much there. Let's close that. Response types we already talked about. Image gen. Yeah, just some subtle tweaks there, checking if GUID is available before trying to do anything with it. Yeah. Getting rid of Stable Diffusion 2.1 because we weren't using it. And that's pretty much it. The last thing to cover is the LLM HTTP Client. So this is a little bit different. All we're doing is being able to accommodate whether we're running the small LLM or the large LLM. This was coded to expect you're always going to be calling the same endpoint. But in our case, this HTTP client can work for whether it's the small LLM or the big LLM. So that's where this override comes in, where we could pass in the URL for the small one. And then also the response format property. And that's just going to get when we're preparing the request body. So if we see here, yeah, that's pretty much all it is. And it's actually really simple because it's already structured the way it needs to. So it's just going to get set as the response format. And that's that. And that should be everything. Let's go ahead and fire up our server and take a look. So I've already got an AC2 set up at this point. I've done it quite a lot. So if you're curious how I did that, check out some other videos of mine. Let's go ahead and Docker compose up -- build it. I've already got the code deployed as well. So this is just going to fire up our stack. Okay, our stack should be started. Let's take a look here. So we can see the services we got. We'll make this a little wider. Come on. No, still. All right, that's fine. So we've got our web, we've got Infinity embedding, and then we've got these two inference ones, and then our OpenSearch and Postgres. Then also what's interesting, NVIDIA SMI, we can see here in this case, we've got plenty of VRAM. This is a G6 instance. We can see the Infinity servers taking up 400 megs with that L12 model. Our small llama is taking up 3 gigs, and then our larger one is taking up just shy of 7 gigs. So, it's again, we are in total using more VRAM because we've got the two different models, but the smaller model should be better at performing those classification tasks. Better in the sense of speed, not necessarily in the quality of classification. So now, with everything started up, if I refresh my browser, you can see here, it's coming in. So if I just do a quick test message, you can see it fired back right away. And the inference, right? So fired, we submitted it. The small model did its thing super quick, I think. And then the large model took over. But if I do image of a cat, the pipeline you can see here, right? So small model did its thing pretty quick. Large model did its thing pretty quick to generate the prompt. And then what we're gonna have to do is load up the diffusion pipeline. So that's gonna take a little bit of time the very first time we run it. And then from there, it's gonna be quicker. So you can see here, I just put an image of a cat, and then it came back with this. And if we actually take a look, because we're using the prompt as the file name, you can kind of infer, pun intended, I suppose, what the language model used. So I put in cat and the language model came back with generate a high resolution image of a domestic cat in a neutral background with a focus on realistic textures from a 45-degree angle with soft lighting. Not too bad, right? Whereas if I were to just put in image, so this is going to be our image only pipeline, and then cat, it'll run through with only cat to work with. And I mean, that's still pretty cool, right? But it's neat that it can fill in the details. Maybe a better example, let's do image of like retro poster. Let's see what it comes back. Directly prompted. Okay, interesting. And then image of a retro poster. Let's see what it says. Keep in mind I'm using Stable Diffusion 1.5 LCM, so that particular one. And all right, well this one, this one's interesting. So yeah, let's do one more test. Let's do cartoony cat on a motorcycle. Okay, and then let's do image of a, image of a cartoony cat on a motorcycle. Let's see what this comes back with. Finally, okay, I wasn't crazy. So you can see by running it through the language model, we got something a little bit more interesting, right? And again, if I were better at prompting, I could probably do this myself, but it's kind of interesting to see what the language model fills in for us. Or if we were to do like image of a, I don't know, vaporwave star space battle. I don't know, something cool like that. Let's see what it comes back for. Yeah, that's kind of cool, right? And if I were to just do directly just putting that in as is, you know, I'm not quite as rich or cool. It would be even better to run this with Flux, I would think, but just using Stable Diffusion 1.5 for performance reasons, I think we're getting some interesting results. So to recap, we're able to just put in a text and the classifier is able to tell whether it's text or whether it wants an image back, and it does it pretty quickly. And then we're using the language model to pre-process a prompt for us and fill in some details. And again, I think it did a pretty good job. So this, dear viewers, is MOM, Mixture of Models. Patent pending. Kidding, of course. I hope you enjoyed it, and I'll see you on the next one.